So this is intended to be in the packet, and for some reason I missed these 2 slides. My bad. I'm sorry. I don't know why. But we need to go through E because it's going to come up again. You're under in. Oh my gosh. So E is a number, a mathy number. It's like pi. It's an irrational, never-ending number. That's a button on the calculator. You don't need to memorize what it is. We don't use it near as frequently as pi, where most of us have it memorized at least to 2 or 3 decimal places. But E is a button on the calculator, and mostly it's used in things like logarithms and in compound interest. So our continuously compound interest, we talked about compound interest yesterday when we did compounded yearly and compounded monthly and compounded semi-annually, and then we got the whole debate of semi-annually versus biannually and all that jazz. So E is what happens when we compound continuously, and it has a slightly different formula, which you've seen before. And it's our count, y'all. My turn. Remember, I'm passing out a quiz today. Remember, I'm passing out the take-home quiz today, so let's get through this. Take-home. Don't panic.
Is it hard?
I don't know, but it might involve an E or 2, so let's talk about it. Y'all, I know it's Friday, and I know we're about to go on break, but we still have things to do. All right, so the continuously compounded interest. It's the one that looks super duper different, but it's actually super easy to do. Our principal times E to the power of our rate times time. Pert. E is a button on the calculator. Our rate, we still use exactly the same way. We put our decimal form of our rate, whatever our unit of time is. This is our principal. E is a number. E is not a variable. We have never done anything like E of X. We have never used E as a letter in place of an equation. I don't know, like any of you ever notice that, but on purpose we don't ever do that because E's a number and it makes all of us kind of twitch. Oh, we love that. There we go. Okay. So we use it in situations like this where Amy was born and her grandparents bought a $5,000 into a savings account, paying 4.6% interest, compounded continuously. If it says compounded continuously, please stop having more conversations while I'm talking. Oh, thank you. So compounded continuously means we use PERT, this guy. So we want to know what the balance will be when she graduates at 18. So how do we set this up? 5,000 E to the power of 0.046, because our 4.6% as a decimal, times 18. So let me see if I can get my calculator pulled up, because we need to type it into the calculator. There it goes. And E is a button on our calculator. On the yellow calculators, you have to hit the green button and then the natural log button. So we're going to do 5,000. To get the E, we hit the green button on the top left.
And then the what?
The natural log right here. It's the LN.
Oh, I put LOG.
That's the common log. Not the common log. We need the natural log so that we get E, and it automatically kicks you up into the exponent because E always has an exponent on it. And we have our 0.046 times 18. 46? I can't remember. Sweet. And it is $11,443.68. So it has more than doubled. $443.68. Okay, so it's very much like the ones we did yesterday. It's just a different formula to go into. So the other formulas all kind of build off of each other. Continuously compounded is its own thing, and it uses E. To what? Unfortunately, we cannot tie a field trip to Panera Bread into our curriculum. Pie. No, I can't tie it into the curriculum. Also, with what funding? Just saying. Legally, no. I do not have a vehicle that will fit the 28 of you. I would have to rent the bus and hire a driver. It would be easier to DoorDash it at that point. All right. We're going to practice solving with E. It's honestly super duper similar to the things we did yesterday, where we have to get the common base and then we can ignore the base. All right? So if the bases are all the same, we just have to play with the exponents. This is this is part of 5.3. This is the last bit of 5.3. We're going to be out of 5.3 after this slide. But we just hadn't done one with an E, and I wanted to make sure we did so before break and the things that we're going to do on break. Okay? Okay? Okay. Remember what I'm passing out at the end of the day today? I wanted to make sure we did the thing with an E before I passed out what I'm passing out today. Are you catching what I'm putting down here? Okay? Okay? Okay. All right. So what we're trying to do is we're trying to get all our bases to be the same and get rid of our exponents. So looking at this left-hand one, which that is the wrong button. Gonna zoom it in because I know we're working in the exponents and I write really small sometimes. So we want to write these to all have the same base. This is already outside of the parentheses and simplified. We have the opposite of x squared, totally fine. How can I write this one as just an E, no parentheses? What do we do with the exponents? Multiply them. Oop, that's not a pen. E to the 2x. And how can I write this one with just an E as a base? E to the -3. Now that they're all common bases, we can play with them like they're made out of Play-Doh. Because the bases aren't really doing anything. Hello, dear. Thank you. What operation is going to be over here between the 2x and the -3? Addition. When we multiply the bases, we add our exponents. So we can also write this as e to the -x squared, e to the 2x plus -3, or just -3. Which means I can ignore the base. It doesn't matter what E is. It doesn't matter that it's being raised to the exponent. All that matters is that the opposite of x squared equals 2x minus 3. It doesn't matter that they're E's. Once we get the base common, we get to ignore it entirely. Oh, really, let me grab you this page because this is not in the packet because I'm bad at printing. All right, so how do we solve this? What do we need to do? Add x squared. So we're going to have 0 equals x squared plus 2x minus 3. Not going to add 3 on both sides. Factor. Or quadratic formula for feeling real froggy. Go for it. But this one does factor. Multiplies to make -3, adds to make +2. 3 and -1. So we have 0 equals x plus 3, x minus 1. And our solutions are -3 and x equals 1. So this one has 2 different solutions that'll do that. Anytime we have an exponent that's squared, we're probably going to wind up with 2 solutions. Okay? We're going to do one more like this. And the right-hand side is a very similar vibe, because we're going to get everything simplified and out of our exponents first. So this becomes e to the, what does this whole side simplify down to? Can you do it in one step? X squared plus 4x equals e to the 12th. I am okay with us skipping steps. You do not have to write as many steps as I write on the board. 100% okay. Because that tells us that x squared plus 4x has to equal 12. It doesn't matter that they're exponents, they have to match. That will make our original expressions equal each other. So what do we do here? Subtract 12 from both sides. X squared plus 4x minus 12 equals 0. Then what? Factor. Minus 12 on the top, 4 on the bottom. What multiplies to make -12, adds to make +4? 6 and -2. X plus 6, x minus 2. So our solutions are and x equals -6. Okay? So they look a little scarier because they have e's and stuff in them, but we treat them exactly the same way. If we needed to get an actual decimal answer, we would just type it in the calculator. We get to use calculators this chapter. Huzzah. We still don't know if we get to on the final. I will let you know as soon as I know. Okay? Questions on E? Because those 2 pages were supposed to be in the packet, and they just weren't. We were supposed to try and get those in yesterday. All right. So we are officially done with 5.2 and 5.3. We're going to look at 4. Yes, ma'am. So we're going to go back into the big proper packet that we were supposed to. And we're going to go to 5.4, which is everybody's favorite, logarithm. We love logarithm. Yeah. All right. Let us see what we remember about logarithms. I will turn the page again. I just wanted to give us a second to write through it. Oh. logarithms. Because it feels like this kind of comes out of nowhere unless you remember the relationship between logarithms and exponentials. My turn, guys. What is the relationship between logarithms and exponentials? You remember? They are inverses of each other. So we spent that whole first section switching the x to the line switch. The logarithm is the inverse operation of raising it to the power of x. So I'm going to switch this back up to the flip fill page because I can write tidier. Is the inverse operation of an exponential function. Don't know why my eye looks so weird. Try that again. We'll do lowercase. A logarithm is the inverse of an exponential function. We have logarithms so we can get the exponent isolated. That is the point of a logarithm, is when we have an x in the exponent and we do the inverse that puts a y in the exponent, and that's super duper gross. So we're going to write out kind of the basic forms of a logarithm. If we have our base raised to a power equaling some argument, the way we write it as a log is a log base b of the argument equals your power. It gets the power out of the exponent. It makes it down into the same row as the regular numbers. And there's a lot of different ways you can write this. Some people do this as an e for exponent. Some do this. Bay. Fine, I'll switch it. I do capital E because we don't like to use little e. Okay. The first time I've ever seen it written as Bay.
Miss Hannah.
Well, Miss Hannah does it differently than me because I've always done a BPA log BAP. BAP. Side-eye. Yes, because they were complaining that we didn't do Bay. It doesn't matter. It's exponent or power. I genuinely do not care. If you like P for power or E for exponent, I don't care. Whatever you guys want to. When I teach it in my regular Algebra 2s is BPA log BAP. Yes. But I don't care. I do not care how you do it. Okay, so our domain for a logarithm is what the range was for our exponential. Remember, this is the inverse function. Exponentials have that limited range because it had that horizontal asymptote. Logarithms then have a limited domain. It's either going to be h to infinity or negative infinity to h, whatever our horizontal transformation is. Our parent function will therefore have a 0. But a logarithmic function has a limited domain. It is not going to be all real numbers. Our range, however, is all real numbers. It goes from negative infinity to positive infinity. It is the domain that an exponential has. Okay? Say it again. The h would be a horizontal transformation like a, h, and k. That same h. We're still going to have a, h, and k in these. But h is our horizontal shift, so it's going to change where our domain goes. Since exponentials have that horizontal asymptote, and an exponential is the inverse, what kind of asymptote is going to have? Vertical asymptote. It has a vertical asymptote, at that horizontal transformation, at x equals h. They have to be. And then our last piece down here is one of those things that if we don't have this rule, things stop functioning, is that the base and argument of a logarithm must always, not optional, be positive. It makes our exponential, like remember how we talked about an exponential has to always be positive or we're getting these weirdo jump things? Logarithms are worse. Don't try and do negative ones. Okay? Because it winds up like with these weird semi-vertical segment, like it's gross. Super gross. Don't do it. So the base and the arguments must always be positive. Always, not optional, non-negotiable, always. Okay? We are going to play around with logarithms for the rest of the day. Yay! Which means we have a couple of very special logarithms that we have to remember. Like the common log and the natural log. So when we were playing with the buttons on the calculator and we hit the wrong one, it had the wrong base. Because the common log, which we just write as log, I always loop my L on the log, otherwise it looks like 10G, just because my handwriting's bad. If you do it like with a straight up little, like that, totally fine. I just habit of mine because otherwise my O's sometimes get big and it looks like 10G. So that's why I loop my log, but that's just me. Okay, so a common log we don't actually write the base on. The common log has a base of, do you remember? Base 10. The reason we love that, it goes quite lovely into the calculator. Quite lovely. It is in fact the first button south of the green button, is the common log. The other one we have that can go on the calculator is the natural log, which would be, surprise, surprise, the one right below it on the calculator, and it's ln. Again, I loop it, otherwise it looks like 1n, which has a base of e. So those are the only two logs we can type into the calculator. The only two. We cannot type any other bases into the calculator. Okay? And so we're going to practice in this little space below here, switching some things around from exponential form to log form. So if we have something like 5 to the 0 equals 1, and we want to switch it around to a log, using our b to the e equals a to our log bay, we're going to write this as log with the same base of 5 of 1 equals 0. The whole point is it pulls our power down.
What is that? Is that 5?
That is a 5. Okay, and that's what we're going to be doing, practicing switching them back and forth repeatedly in the next thing. We're going to switch from log form to powers and from powers to logs. Okay. And I have them written on your slides with P because that's the way I'm used to it. But you can cross it out and put it as an E if you want. I'll switch them up here. Y'all like E so much, except it needs to be capital E. I'm switching it over here so that you have your bay. There. Better. Okay, so we're just going to switch them around. So negative 2 equals log base 4 of 1/16. How do we write this as an exponent? As an exponent. Yep. So our base is 4. Our power, or our exponent, is negative 2. And it equals our argument of 1/16. The only piece of this that can be negative is that exponent. And that's all we're doing with that. This, right, 4 to the negative 2 is 1/16. How about the log base 7 on the right? How do we write that one? 7 to the power of 2, 7 squared, equals 49. Yes, at this stage, I hope it's easy. It is review, Tommy. How do you write the bottom one on the left? 2 to the 0 equals 1. And the last one down here, 3 cubed equals 27. Okay, vaguely familiar? Good, because now we're going to go the other direction. Exponentials back into log form. Other way. I'm not switching the formulas again because it has to get super tiny. All right, so this 5 cubed, how do we write this as a log? Log base what? Base 5. The base of our exponential is the base of our log. What is our argument? 125. And it's going to equal our exponent of 3. The whole point is for the power to be isolated, if that helps you remember. I want the power away from everybody else, so he's alone. So this next one, the 3 squared, is going to be log base 3 of 9 equals 2. The base of the exponent is the base of our log. Our power goes on the other side. Process of elimination. The 9 is here. Okay. 2 more of these before we kick it up a notch. Log base 2 of, what's our argument on this one? 125 equals 5. Little curveball over here. Log base E of y equals x. Let's simplify this a little. Log base E, how else can I write that? The natural log. We can do ln of y equals x. So if we have log base E, we can write it as ln. If we have log base 10, we just write log. You don't have to put the 10. Okay? Questions on switching between the forms? Awesome sauce. We were doing super awesome on time and I love it. Because now we're going to practice evaluating just a smidge. And we do not need to use a calculator for this. Most of these we can't type in the calculator because they have bases. So we got to be able to do it without a calculator. So what we have here is we have log base 2 of 1/16 is what?
-4.
Hang on, my brain stopped working right. It's the day before break, my brain's checked out. It is gonna be -4. How do you know that?
My calculator told me.
Yeah, but not all calculators have that. So how will we do it if your calculator runs out of battery?
You will substitute the exponent.
2 to some exponent equals 1/16. 2 to the what is 1/16? 2 to the -4. Okay? So tell me, put your calculator down. I did specifically say without a calculator. So this is log base 12 of 144. 2. 12 to the what? I'm going to put an exclamation point. Question mark. There we go. Equals 144. Question mark equals 2. What's our base on this one? 10. So 10 to the what is 1,000? 3. All right. Log base 4 of 1/64. -3. Okay. Uh, 4 to the what equals 64, or 1/64. And so 4 to the what is 64, 4 cubed is 64. Oh, the 1,000 is same thing. 10 to the what equals 1,000. When you're doing multiples of 10, you just count the zeros. There's 1, 2, 3 zeros. 10 times itself 3 times. So give us that many zeros. Good questions. Okay. The next two are a smidge harder. All right, are we ready for the next two? Our last two of the solving or evaluating, because they're not solving because they don't have an equal sign. It's evaluating. Okay. So look at each log individually. Log base 3 of 9 is what? So just look at, hang on, this. What is log base 3 of 9? 2. 3 squared gives us 9. What is log base 2 of 8? 3. What is log base 4 of 1/16? -2. So we have 2 plus 3 minus -2. 2 plus 3 minus -2 is 7. So zoom it in, do each one individually, and then do your operation. Okay? This one's a little grosser. Log base 5 of 5 is 1 minus 3. Hard one. So this is log base e of e to the 1/3. So yeah, our log base e of e, that piece cancels out. So it's just 1/3. I know, I was just explaining it. I'm not saying you're wrong if I start explaining it. I'm just explaining it for the people who didn't guess it. Great. 1 minus 3 plus 1/3. Not 11. -1 2/3. So 1 minus 3 is -2 plus 1/3 is -1 2/3. When your base and your argument are the same, it's just whatever your exponent is. Like we have here, 5 base 5. We got a 1. That's what the exponent was here. Okay? Last 2, we're probably only going to get through one of them. And that's okay. Like, I totally planned for that. Because this is where we start using our logs. And this is actually a real thing. The formula for how you figure out what f-stop setting you use on a camera is based off of this, I'm told. It has to do with the amount of time the shutter is open. Because professional photographers adjust that so that the pictures look all certified. So if you're gonna be paid to be taking pictures, you're gonna have to know how to change all the things. Okay? So it's N is the amount of, or P is the amount of sunlight. If it is measured as 16, what setting should you put the f-stop on? Okay, so all this is they're saying the sunlight is measured at 16 in whatever units they're using. I'm not entirely sure, but I think they have a tool that says it's 16. Plug it into the formula. So P is the amount of sunlight. So P equals 16. So what we're told here is log base 2 of 16 equals what? So what does N equal? This says 2 to the N equals 16. So switch it around if you need to, but then N equals 4. So our f-stop setting should be 4. We totally have time to do the last one. We love it. We totally do. It puts us in a good place for when we come back from break. We gonna do it. We have 4 minutes. We got time. We have 4 minutes. They don't take super long. Okay, at Earth's surface, air pressure is decreased for each mile of altitude. The atmospheric pressure P can be modeled by this log, where X is your altitude in miles. Find the number of miles it would take for the atmospheric pressure to measure 7 atmospheres. So it's on the other side now. 7 is our atmospheres. That's our pressure. So we have 7 equals log base 0.4 of X. Oops, sorry. So switch it around from log form back to exponential. Our base is 0.4. What is our power? 7 equals X. What is X? 0.0016. Give me whatever you got. 16384 miles. Okay? All right. So, I'm going to pass out the take-home quiz. It is due when you come back. Here is, I believe this is our second to last quiz. I think we only have one more. Take the whole break to do it. See if I can get it in before I get through.
Add that to the list.
There you go. The first two teachers didn't work any attention for you. Have a great break! Take some time to relax. It is important.
It is important.
It is important that you take some time to relax.
Little marshmallow guy fell over.
To be fair, he's technically made of body fat.
He looks like a marshmallow. I have a question.
He's called an adipose. He's a monster from Doctor Who.
Do you know when, like, it sounds weird, but do you know when Christmas break is?
The 22nd is
22nd.
when it starts for you. That's my teacher work day.
22nd to when?
To the second week.
Can
Like,
I-
I want to say it's January 8th
Can I
or
write this
10th. Yeah, hang on. Let me pull out the calendar then and give you proper actual dates. That's not the calendar. It's over here. Boop. So, December. The last day of school is the 21st. So your first day off is the 22nd. And the day we come back is January 8th.
Is the take-home quiz online or paper?
Paper. I just handed it out.
Oh. I'll have to take that one.
Okay.
Alright, thank you very much.
Also,